You know, every single time you send an email, buy something online, or even just browse a website, there's this invisible shield protecting your information. That shield? It's modern cryptography. So today, we're going to pop open the toolbox and take a look at the fundamental tools that actually build this digital trust, piece by piece. And we'll start with the most basic question of all. Right? It's a question we've all wondered about. We see that little lock icon and we're told our connection is secure, but what does that really mean? How can you possibly send a private message across a global network where, theoretically, anyone could be listening in? Well, the answer lies in some incredibly clever math that acts like locks, seals, and secret handshakes. So in this explainer, we're going to build our digital trust toolkit together. We're going to add 4 essential components. We'll start with the digital fingerprint, which is called SHA. Then we'll move on to the digital wax seal of HMAC. After that, we'll unlock the magic of public and private keys with something called RSA. And finally, we'll see how it's possible to create a secret right out in the open using Diffie-Hellman. Okay, first up, let's tackle a really fundamental problem: integrity. How do you know that the file you just downloaded is the exact same one the developer uploaded? That it has no errors, no malicious changes snuck in? Well, for that, you need a unique digital fingerprint. The basic idea behind creating this fingerprint, or what's called a hash, is actually pretty simple. A process called a hash function takes all your data, chops it into little blocks, and just mixes them all together. This super simple version here just rotates the result and uses a basic math operation to combine it with the next block, over and over again. The goal is always the same: produce one single, fixed size value at the very end. But as you might guess, there's a big problem with an approach this simple. Yeah, there's the problem. While a simple hash like that might be fine for, say, checking for accidental glitches in the data, for actual security, it's basically useless. An attacker could pretty easily create a different, malicious file that produces the exact same fingerprint. That's called a collision. And if that happens, your fingerprint is completely worthless as a security check. So we need something much, much stronger. And this is the solution: the Secure Hash Algorithm, or SHA. This is the industry standard. Now look at a modern version like SHA-512. That security bits column, that 256, tells you how hard it is for an attacker to break it. And to put 256 bits into perspective, 2 to the power of 256 is a number so ridiculously huge, it's larger than the estimated number of atoms in the entire known universe. It is practically impossible for all the supercomputers in the world combined to find a collision. And this isn't just some abstract concept. If you've ever downloaded a big piece of software and seen that long string of random-looking characters called a checksum or a hash that they tell you to verify, yep, you've seen SHA in action. That's the real-world tool that guarantees the file you got is the file you were supposed to get. So SHA takes care of integrity, knowing the data hasn't changed. Awesome. But that brings up the next obvious question. What about authenticity? How do we prove who the data is actually from? That's where the next tool in our kit comes in. Okay, here's the next problem we have to solve. A SHA hash is totally public. So if an attacker intercepts your message and changes it, what's to stop them from just calculating a brand new, perfectly valid SHA hash for their fake message and sending that along instead? The person on the other end would have no idea anything was wrong. To fix this, we need to add a secret ingredient. And that secret ingredient is called an HMAC, which stands for Hash-Based Message Authentication Code. Honestly, the analogy of wax seal is perfect. It proves 2 things. Not only that the message is intact, but because that specific seal could only be created with a secret key that only you and the sender share, it also proves who sent it. Integrity and authenticity all in one. So how does it work its magic? Well, it's this clever double hashing process. First, it mixes the secret key with the message and runs that whole thing through a hash function, like the SHA we just talked about. But it doesn't stop there. It then takes the key again, mixes it with that first hash result, and hashes it a second time. This process weaves the secret key into the message's fingerprint so tightly that it's absolutely impossible to fake it without knowing that original secret key. All right, so now we can guarantee a message hasn't been changed, and we know who sent it. But notice something? We haven't actually hidden the message itself. Everything we've talked about so far could be sent in plain text for anyone to read. To get real privacy or confidentiality, we need our third tool, encryption. Now, before we get to the really cool part, we have to understand this one crucial idea. There's symmetric cryptography, which is like a safe. The same exact key locks it and unlocks it. It's simple, but now you have the new problem of how to share that one key securely. Then there's asymmetric cryptography. This is different. It uses two keys, a public key you can give to anyone and a private key you keep totally secret. The public key can only lock the message, only your private key can unlock it. Think of it like a mailbox. Anyone can drop a letter in the mail slot, but only you have the key to open it up and read what's inside. And the most famous system that does this is RSA. It's all based on some really clever math around how hard it is to factor huge numbers. It honestly feels like a magic trick, so let's just walk through a quick example. Okay, let's say the secret message we want to send is just the number 88. This is our plain text. To send it, we need the public key of the person we're sending it to. Let's say their key is made of the numbers 7 and 187. We then perform this calculation you see on the screen. The important thing is, anyone can do this math with the public key, and it completely scrambles our number 88 into something totally different. And the result is 11. That's our ciphertext. Our original message, 88, is now completely gone. If you were an eavesdropper and you just saw the number 11, you would have absolutely no idea where it came from. Now, our friend receives the number 11. They pull out their private key, which only they have, in this case, the numbers 23 and 187. They perform a similar looking calculation, but with their own secret number. And boom, like magic, out pops the original message, 88. This is the core of so much of our online security, the ability for anyone in the world to lock a message, but only one specific person to unlock it. And the security of this magic just depends on how huge those numbers are, which is why you hear about key lengths of 2048 or even 4096 bits. So, our toolkit is almost complete. We can check integrity, prove authenticity, and ensure confidentiality. But there's one last big puzzle. All of this depends on having secret keys. So how do two people who have never even met create a shared secret key over an insecure network where everybody can hear every word they're saying? This is the famous Diffie-Hellman key exchange problem, and the solution is like a magic trick with paint. Imagine you and a friend publicly agree on a common starting color, let's say yellow. Then you each secretly choose your own private color. You mix your private color with the public yellow and send that new mixture across the room. Your friend does the same. Now, you each take the blob of paint you just received and mix in your own secret color one more time. And magically, you both end up with the exact same final secret color, a color that no one else watching could possibly figure out. But this public process has one big critical vulnerability. And that vulnerability is the classic man-in-the-middle attack. Because that initial exchange doesn't prove who you're talking to, an attacker can just sit right in the middle of your conversation. So Darth, the attacker, intercepts Alice's public info and sends his own to Bob. He does the same thing with Bob's info back to Alice. The result? The attacker creates one secret key with Alice and a totally different secret key with Bob, all while Alice and Bob think they're talking directly to each other. The attacker can now read and even change every single message they send. And this is why key exchanges in the real world are always paired with digital certificates to prove identities, but that's a topic for another day. So there you have it, the 4 core tools in our digital trust toolkit. We've got SHA, the digital fingerprint to make sure data hasn't been messed with, HMAC, the wax seal to prove it's from the right person, RSA, the public mailbox to keep the contents private, and Diffie-Hellman, the secret handshake to get the whole secure conversation started in the first place. And that brings us to a final, really important thought. Everything we've talked about, our entire digital world of secrets, is built on one single assumption, that certain math problems are just too hard for our current computers to solve in any reasonable amount of time. But what happens when that's no longer true? With the rise of things like quantum computing, a powerful enough machine could theoretically break the math behind RSA in just a few minutes, turning all our private mailboxes into open books. The very foundations of our toolkit are being challenged, and it's pushing us into a brand new race to create the next generation of unbreakable secrets.